Same thing, detailed. Okay, so that wraps up fly-by-wire. The last kind of control actuation setup we've got is fly-by-light. And so again, yet another one, no physical connection between the stick or the yoke and surface. It still relies on electrical. We have to have electrical to run the computers, to run the fiber optic transmitters and receivers. And so we have to have that. If it's fly-by-light controlling hydraulics, we would need hydraulic systems. But now we use fiber optics to send signals to flight controls. They also can provide the feedback loop. However, it's still an electric feedback loop in that you have the VDTs, RVDTs, LVDTs that produce the signal that goes to a computer that then goes to a fiber optic transmitter or fiber optic transmitter transceiver. To provide that feedback loop. And so these can be hydraulic or electric. Majority of the ones I've seen are electric in nature. The advantage to this, they're not really any faster per se. You know, electricity and light travel at essentially the same speed. There are some advantages. They do say there are some speed advantages, but for civilian aircraft, minimal. Where you see these more is militaries use these, and a big part of it is fiber optics don't have to be shielded from EMP, and so if you're worried about electromagnetic pulse taking out your aircraft, you can harden the cases around the computers and that kind of thing, but you don't have to necessarily run EMP insulation along all your wiring and everything like that. So they're less likely to be affected by interference. And so that's where I've seen them on the civilian aircraft, is particularly if you have to run a signal through an area where it would be prone to electrical interference, right? Because any wire can act as an antenna. You can use a fiber optic based system instead of an electric system. And so they are there, don't see them very often. We had one airplane I worked on had one set up with this, and it ran the spoilers. It was tied into our spoiler system. I never could get an answer from our avionics guy our avionics team, why this was fly-by-light rather than fly-by-wire, but that's what it was. So to summarize, we have our 6 different ones here. And mechanical, the first 3, well, mechanical is not part of it, but the ones with hydraulics here are power control unit operated, are mechanical with hydraulic boost, mechanical control with hydraulic actuation, and electrical control with hydraulic actuation. And then the ones that use electrical control with hydraulic actuation, electrical control of electrical actuation, those are considered your fly-by-wire systems. And then finally, light control, whether it's hydraulic or electrical actuation, is called a fly-by-light system. Okay, so that's kind of the summary slide that ties all that together. When we put these all into an airplane, we use more than one system or more than one method. So most aircraft employ more than one control method and actuation system. And even individual flight controls can sometimes employ more than one of these. So if we kind of look at this diagram, some of the things you'll notice here, the first thing I'll show is in the gray box here. Here are our inputs in the cockpit, in the flight deck. So we've got things like speed brakes, control columns, pedals, trim switches, flaps and slats, right? And it shows how the signals are sent out. There are a couple others here. We've got the servo roll, servo pitch, servo yaw. And what do you think those are for that provide an input? What is an input servo? So we talked about servos out at the flight controls, but what could provide an input, a servo input? Where do they get? Any idea? What's the line coming to them from? Autopilot, that's your auto flight control system, right? So it has the ability to, in this case, in this aircraft, control roll, pitch, and yaw. Most of your transport aircraft are 3-axis autopilot. There's very few, none that I can think of on a modern aircraft that is not a 3-axis autopilot. Everyone's familiar with that. But some smaller airplanes may only have a 2 or a 1-axis autopilot. Can only control ailerons or can only control rudder, for instance. But anything on a large aircraft is going to be 3-axis. But you can see here we have our inputs, and for rudder, yaw, and for pitch control, we are fully fly-by-wire. So there is a little bit of a mechanical linkage here. These tan lines are mechanical to our LVDTs, but then from there, the pitch and yaw LVDTs go to the the computers that essentially control that are going to perform that control and feedback loop. And those send signals out to the elevators and rudders. You can see there's a feedback here. There's a two-way arrow going back that, you could look at it as the input, control, and then feedback. Okay. It can also get some information from the flight control module up top. Get information, send it out, and that's where some of that, changing the different laws and changing how the airplane behaves based on flight conditions can come from. It can provide an additional input, that blue line there. And that's what they call the CAN bus. It's the bus architecture, right? So they're talking to each other over a bus. But you can see on this aircraft as well, there is for roll, this is that Embraer 175, that one I showed. Remember I said the only thing on it that is controlled mechanically was those ailerons. I showed the cables and bell cranks and everything in the colored diagram. So here is that illustrated with a mechanical control of the ailerons, but it can also provide roll control through fly-by-wire. You can see there's roll LVDTs that go to this flight control module and then ultimately control the spoilers, the flight spoilers or spoilerons. And so that one's got a dual mode of controlling roll, mechanically with hydraulic. Now they're all hydraulically. These spoilers, ailerons, elevator, rudder, those are all hydraulically driven, hydraulically actuated. But they're controlled, some of them are controlled with fly-by-wire electrically, some of them are controlled with a mechanical linkage, just the ailerons in this case. You can see the trim system, it's fly-by-wire essentially. It has the HSA here is horizontal stab actuator. That's an electric motor. It's a fancy name for an electric motor that drives the horizontal stabilizer. That's electrical control. And that's pretty common. Most transport aircraft have had electrical stabilizer trim controls since probably about the late 80s, 1990s. Okay. Flaps and slats, electrical control. Okay. Now the 727, that's still mechanical control. That flap handle has cables going from it and stuff. That's old school. Okay. Speed brakes, same thing, can control spoilers. So you can see there's a lot of fly-by-wire on here with a little bit of kind of mechanical reversionary going to the aileron. Okay. With all of these systems, with the exception of a purely mechanical system, we have to provide the operators, the crew, with artificial feel. Because when you're flying, when you're operating an aircraft, they're using their various senses, right? You're using sight, look outside, although oftentimes sight's mainly used to look at instruments. Okay, you're using sound, you can hear things, right? You're using your sense of balance and direction, although that can be easily fooled. Has anyone ever flown in instrument conditions? Ever had any experience with that? A little bit? Did you fly or you were a passenger? Totally disoriented? A little bit? You didn't know which way was up or down? Right? The other thing we have though is when we're operating, we want to make sure that we can feel the flight control. When you're in a small airplane, if you go in one of the Cirrus, the Seminole, one of these, as you're flying, the way the stick feels, the way the rudder pedal feels, is going to change and be affected by the airplane and by it flying through the sky. Okay? The harder you pull back on a flight control, the harder it pushes you back towards neutral. Right? Think about like an elevator. If I tip my elevator up a little bit, you know, there's air hitting it, right, coming out the front. It's going to try to push it back to streamlined. Right? You tip it up a little bit, there's going to be a little bit of force there. You tip it up full travel, there's going to be a heck of a lot more air hitting that thing and really trying to push it back down. So that's going to be fed back to the stick or the control column. Okay? Same thing with the aileron, same thing with the rudder. You kick the rudder one way or the other. The faster you're going, the harder it's going to try to push that back to neutral. And the further you deflect it, the more air is hitting it trying to push it back to neutral. Okay? If we eliminate that mechanical linkage altogether, or if we're in a situation where the hydraulics are what's moving it, we will not get any of that feedback back through our control inputs. Because the hydraulics are taking all that force, or the electrical actuator is taking all that force. And you lose the ability to feel what the airplane's doing. Okay, that's one part of it. The other thing that it can cause is humans are really, really bad at holding things in a certain position if there's really no feedback and they aren't actually looking at it. If you try to hold your hand in a set position outside of your field of view, if you hold your arms up like this, what's going to happen over time? If I'm not paying attention to them, fatigue is going to cause my arms to do what? Over time, they're probably going to drop. Right? Same thing. If you're sitting there holding a stick like this, you've got the weight, the weight of your arms on your elbows, right? What do you think I'll do over time if there's really no feel on it? I'm going to want to drop my elbows down onto the armrest, right? And I'll end up pulling back. And you may not, an operator, a pilot, may not realize they're doing that. And it may cause the pitch of the plane to increase so subtly that they may not realize the plane is starting to pitch up. Until the point, what happens? We continue to pitch up and up and up and up. Eventually, what's the plane going to do? You're going to stall. Now, in a small plane, before it stalls, what happens? What do we start to get? You get vibration, it buffets. And they'll feel that. It'll push back, the stick will start to shake. Okay? In a big airplane, they put a little motor. We all played with the stick shaker when you guys did haptic feedback, or haptic, when we were in the 727 and you guys tested the different indication systems. One of them was haptic. You also stick shaker shake, right? You look for the little wheel to spin, right? That shaking is to simulate that. That's a type of artificial feel that simulates that buffeting when you get close to a stall. Okay? But there's nothing there. You've also noticed when you pull back on the columns or push on them, right? Are they easy to move? Do they just move around? Or is there resistance there? That's the feel system, and that is to give you that. So it provides tactile feedback, so you know, but we have to do it a few different ways. So the simplest way is mechanical, things like cams, rollers, and springs. Okay? Eventually, then we realize, okay, you put cams, rollers, and springs on, there's only so much you can do. The feel, for instance, the feel will always be the same. So say you have a spring that you have to pull back against, right, for pitch. When you have a spring like that, the harder you pull, the more it's going to try to pull you forward. Okay, good. So that matches what an elevator feels like. You pull back a little bit, there's not a lot of resistance. You pull back harder, there's a lot more resistance, right, as you stretch the spring. But if all you have is a spring, that's going to be the same whether you're traveling 200 miles an hour or 400 miles an hour, right? Are the forces on that elevator the same at 200 miles an hour as they are at 400 miles an hour? No. So by going to these hydraulic and electrical actuators, we can now adjust that force curve with changes in aircraft speed, altitude, air density, all those kind of things. And so we can make this feel adaptive. The feel system can be adaptive based on the conditions that the plane's flying in. Okay. So here is an example of a rudder pedal. You can see we got rudder pedals going through linkages. It goes to the servo valve. This is a mechanically controlled, hydraulically actuated example. And what they've added here, you can see, is this little bell crank where when this gets pushed or pulled, it rocks this little Y. And as it rocks the Y, it kind of pushes down on this roller, right? That stretches a spring. So that's a form. Rather than connecting the spring directly here, they've got this roller that kind of does it. And so it looks something like this. So that's kind of your most basic artificial mechanical feel system. You can see there's nothing here that can change. You know, no matter if the plane's going slow or fast, you're always going to get the same feeling out of your rudder pedals, out of your elevator, out of your aileron control. But then what we can do is add a way to change essentially the spring tension here. We increase the spring tension when the plane's flying faster. We decrease the spring tension when the plane's flying slower, and that will simulate that changing feel over time. And so a way to do that here is with this is an actuator, and these can be hydraulic or electric, that essentially can put a little bit more or a little bit less preload on that spring. So when the plane's flying slower, you take off the spring, so there's less initial force to overcome. As the plane flies faster, this little actuator here with airspeed and altitude data will put additional force on the spring so that even at smaller deflections, you'll feel a greater force to simulate what that flight control, the effects, the forces on the flight control are at those higher speeds. Okay. That's a mechanical one where it can do that spring feel. Hydraulically, we can also do it with a servo valve type system. So here we've got pitot and static that move a little pilot valve there, a little spool type pilot valve. And we have a pressure side and a return side, but it's not necessarily cutting one off. It's really allowed a bypass from the pressure of the return. So when we want to be able to move the flight control more easily, we reduce the pressure on our feel actuator over here by allowing a certain amount of fluid to bypass between pressure and return. We don't want to hydraulically lock it, then we wouldn't be able to move our flight control, right? But as our airspeed increases, this will block off more and more of that passage between the pressure and the return, which will create a higher pressure on this feel device and thus provide more resistance to being able to move the flight control in order to simulate those forces that are lost when we no longer have a mechanical connection to the flight control and provide that feedback to the crew. Electrically works, this is essentially an electrical one by changing the spring tension, okay? So that's our artificial feel system and the importance behind it in order to help the crew feel the airplane, because the feel of it is an important part of the body understanding what's going on. It can be tricked, especially when you can't see anything, but pilots are taught to trust their instruments in that case. But they still need to be able to feel what they're doing, without having to stare. We don't want them staring down at the stick the whole time to make sure they're holding it centered, right? We want them to know if they're starting to drift one way or the other. Or if a pilot's got like one leg longer than the other, right? You don't want them always flying in a big right-hand arc or something, right? So just a review of flight controls. You should all be very, very familiar with these by now. Ailerons provide roll along the longitudinal axis, longest axis, right, length of the airplane. Elevators provide pitch around the lateral axis, lateral left to right. And then rudder is your yaw around the vertical axis. Okay. You've seen that ever since you were in what, like 1220, AVS 1220, right? Okay. I remember talking about that when I taught 1220. Okay. But as we get into these bigger airplanes, now we got to look at more high lift devices. And you may have seen, small airplanes, you're probably real familiar with flaps, but you haven't necessarily seen some of the other high lift devices that we need to apply. Flaps aren't quite enough. When we get to these big aircraft, just the flaps alone can't provide enough of a difference. And so now we start adding things on, not just flaps, we make the flaps more complicated. We add slots and multiple panels, okay? On the leading edges, we can add slats. This is a slat right here, okay, a leading edge slat. A leading edge flap is typically a Kruger flap is one that comes down from the bottom of the wing. It looks, the 727 has it on the inboard part. You know, when we were under there doing fuel and there were those panels kind of hanging down, you can grab them, pull them out. Those are a Kruger flap. Those are a leading edge flap. A leading edge slat looks a lot like a trailing edge flap, just on the front of the wing. Okay, so when you're looking at the difference, what's the difference between leading edge flaps and slats? Here's a leading edge slat. A leading edge flap are the Kruger ones that drop down. I'll show you a video here in a sec that has those. And then our trailing edge, those are always called flaps typically. Different ways these can be actuated. There were, back in the day, air pressure ones, where this leading edge, not this one is hydraulically driven, but there were aircraft back in the day where if they were sitting on the ground, they weren't moving, you'd see these things droop down all the time. And then as the plane gets moving faster, right, at takeoff speeds and lower speeds, they stay down. But then as it starts flying faster, the air hitting the leading edge would actually shove it back up flush with the leading edge of the wing. So that's when I say they're air pressure activated. It's purely the air hitting the leading edge at higher airspeeds pushes it up flush with the wing. Mechanical is things driven by things like ball screw actuators, big nut that's turned by a motor, and then you've got a screw. That's what's inside of these canoes right here. The ball screw actuators. You saw these 727 when I dropped them. You saw those big silver jack screws there. Okay, those are mechanical. Electric typically is more of driving the actuator. Electric motors. They can be hydraulics. These ones here are rack and pinion. These are hydraulic. I believe these are hydraulic here. This is an Airbus. I can't remember which one. And oftentimes they're a combination of the two. So here I've got the 727, because our flaps aren't playing nice right now, I have a video pulled up here. So certainly more complicated than the normal kind of just the standard flaps you guys are all very familiar with seeing around the aircraft we have here. Some of the other controls we have, trim. You've seen trim in the form of small trim tabs typically. Larger aircraft are going to have more complicated trim systems. But the big thing is reducing pilot workload, maintaining level flight, increasing fuel efficiency. You know, if the plane isn't trimmed properly, you don't want the crew to have to sit there and constantly be holding, if the pitch trim is off, be holding the nose up, or constantly be holding a little bit of left or right aileron, right? So the trim allows us to get the plane neutral, flying level, flat, straight, while it's in the air based on changes in weight. And this is particularly important in large transport aircraft because they have a swept wing design. You got a couple different things that are going to happen. Why do you think we have to trim these throughout flight? What does the swept wing have to do with it? This is primarily pitch trim. What do you know about a swept wing? Aerodynamics 101. Anyone? They're efficient at high speed. Okay. What about as speed changes? Do you know what happens with a swept wing as you change speed? The what? The location of the center of lift changes. Okay. So, you go from these small aircraft, lightweight or straight wing, right? They can kind of trim them and they're probably going to be okay. But with a transport aircraft, as you speed up or slow down, that center of lift is going to move. And so that's going to change how the airplane is going to want to pitch. So pitch trim is critically important on these. In fact, that's a system called Mach trim. It monitors the Mach number. And Mach doesn't necessarily have to mean above the speed of sound. A lot of these fly at like Mach 0.92 or Mach 0.76, right? 3/4 of the speed of sound, that kind of thing. So, there's Mach trim systems that automatically adjust the pitch based on airspeed. The other thing that happens is throughout flight, the airplane's going to burn fuel. And a swept wing airplane, what does that mean? It gets lighter. It gets faster, maybe. But what else? Swept wing airplane? As the fuel burns, where does the fuel move? Where does the fuel center of mass move? It's going to move towards the center, but what else is it going to do? It's going to move forward, right? Because the fuel that's at the wing tips, which are further back, is going to be burned away, while there's still fuel closer to the wing root, which is further forward. So throughout flight, the center of mass is going to change because that. So pitch trim is probably the most important of any trim on these airplanes. One, you want to prevent it from getting into a stall position, but two is there are elements of how they fly that affect pitch trim more than a small airplane or a straight wing airplane is going to see. And so this can be done a few different ways. Small planes tend to use trim tabs. You really don't see these as much on larger aircraft. They're not as efficient. And so we get things called surface trim. And the stabilizer is one of these. For pitch trim, for instance, we don't just trim the elevator. We don't just trim a trim tab. Transport aircraft, we actually move the entire horizontal stabilizer. We change the angle of incidence of the entire stabilizer. And so we have our stab trim system. Okay? So that's a way we can do it. We can actually move the entire So that's the stab trim system. Some of your other trims. So often what these have is, because a trim tab really doesn't do much for you on a hydraulic aircraft, right? Because it would have to overcome hydraulic lock if you had a trim tab on there. So what's often done is we can adjust to the flight control neutral position by being able to adjust like linkage length. And so what that means is, if we add somewhere in here, if we add a little like electric actuator, if we make this a little bit longer or a little bit shorter, that's going to adjust the input to our servo actuator to create a new neutral position, right? So that's one way to mechanically move the mount point. Or we can move the mount point here. Or we can move even this mount point a little bit. So we can readjust, we can put things into the different points in the mechanical linkage that skew the neutral position for our flight control. That's one way of doing trim. Another way is electrical. So here's our diagram again. And this is how, with fly-by-wire aircraft, what we can do is we can have a computer-generated signal that we feed in along with our signal coming from our input VDTs. And if we put, say we want to go nose up slightly, we add a little bit of positive, in this case, we'd add a little bit of positive input signal, and that would cause this to move up just a little bit, even though this is in the neutral position. So, on fly-by-wire aircraft, that can be adjusted by doing that. So alter the signals, basically. Put some interference in there that moves it one way or the other. Okay. Kind of the last system we'll look at is our spoilers. And I've mentioned these before. Spoilers spoil lift. They're on top of the wing, and they screw up the airflow over the top of the wing on purpose. And when we do that, we lose lift on the wing where they are deployed. And we can either do that on both sides to lose lift across the board, or we can lift them up on one side or the other, which will cause the lift on one wing to be reduced, and it'll make the airplane roll. So flight spoilers have those variable deflections, and they lift on both sides. So a flight spoiler is often used, so this is both sides. These are even. This is to help with descent. We pop up the spoilers a little bit on both sides, reduces the amount of lift available to the airplane. The airplane's going to start to sink. Okay, that's a flight spoiler. Even side to side. Ground spoilers are also even side to side, and here they are shown in that deployed position where the airplane has just touched down, the wheels hit, they all pop up in the air, and they help eliminate lift in order to get as much force down onto the wheels as possible to make the brakes more effective, prevent the airplane from bouncing back up in the air, and really hold it down on the ground. So they increase the downforce for braking, they reduce the chances of the plane going airborne again. And again, these are, in these cases, they would be popped up evenly side to side. We can also use them for roll control. And now instead of doing evenly side to side, we only pop them up on one side or the other. So they deploy to assist the ailerons. So the downward moving wing, they deploy variably, a little bit for a little bit of roll, a lot more for a lot of roll, in order to assist the ailerons. Or in some cases, this is what provides roll control at cruise speeds while the ailerons stay neutral, almost entirely neutral. And those are known as spoilerons or roll control spoilers. And finally, speed brakes, another one that deploys evenly side to side. They work a lot like the flight spoilers, but now the goal is, instead of making the airplane sink, it's to slow it down. So if we go nose down, we start to raise them a little bit. It does the same thing. So a lot of your flight spoilers also can serve as speed brakes. And that gets into the term multifunction spoilers. So many of these panels have a multifunction role. These ones here, right, outboard, you can see it's deployed when it's in ground lift dump, fully deployed. Here it's in a partial deploy, probably for roll control. So those are a multifunction spoiler. They can serve as a spoileron, a roll control spoiler. They can probably serve as a speed brake, and they can serve as a ground spoiler. You get those. Question? They can be both. Many of them, most of them are probably hydraulic. There are some that are electrically actuated. So it depends on the aircraft manufacturer and how they decide to drive them. They can be electrical. They can be, most of them though are hydraulic. So you've got, I don't know if you can quite see, there are hydraulic actuators under here. They're kind of hard to see.